Once again, welcome to Physics STPM. I am Mr. Kung, your instructor. Okay, let's start. We're now continuing on topic 4, work, energy, and power. Right? As I said, you can either draw, use the computer, use PowerPoint to summarize all the formulas that you need to remember, all the definitions, or draw a piece of paper for each topic to define work. These are defining equation. Remember, these are two vector quantity. This is a small distance, small displacement, ds. There's your force. Right? Or to find the magnitude, there's the magnitude. And for spring, our force equals to kx. K is your spring constant. And the energy stored in spring is half kx squared. Then we have derived formula for kinetic energy and formula for potential energy. And then we say that in any situation, you can understand what's happening and write the work energy theorem. Like in this case, right? When you throw a ball up, no air resistance. It's just a loss in kinetic energy, gain in potential energy. Okay, let's try. We are now in this topic 4.2. Let's complete it. Right? This one is the graph of potential energy and kinetic energy when dropping a ball. No air resistance. Okay, stop the video and have a go at this question. Try that. Example 4.3. Change in kinetic energy. Tennis ball of mass 0.9 kilogram is hit at a velocity of 30 meters per second towards a wall. It strikes it perpendicular and rebounds at a velocity of 25 meters per second. Calculate the initial kinetic energy of the tennis ball, the change in kinetic energy of the tennis ball. Comment on your answer. Okay, draw a rough picture. Solve the equation. Understand in your mind or draw a rough picture. Right? There's initial velocity after collision, final velocity. That's the question. Right? Initial velocity is just your half mu square, initial speed, square that. And change is yours. You can take a final velocity minus initial velocity, it doesn't matter. If there's a negative sign, it shows there's a decrease because you're comparing the final to the initial. But if you want positive, you use initial kinetic energy minus your final kinetic energy. And this is in elastic collision, where there is a decrease in kinetic energy after collision. Okay, try this one. A car of mass 2,200 kilograms moving at a velocity of 80 meters per second decelerates to 10 meters per second in a distance of 250 meters. Right? Calculate the initial kinetic energy. Right? Simple thing, you should be able to calculate that. Half mv square of nu square. Put in that's your mass, and that's the initial speed. Right? Using your calculator. Work done by retarding force, where there's a decrease in kinetic energy, you should be able to write down the work energy theorem. Work done equals the loss in kinetic energy. So work done is just your force or friction, friction or retarding force. So work done is loss in kinetic energy, the initial kinetic energy, which I calculate, minus the final kinetic energy, half m v squared. And retarding force, work done is just your force and distance. So that is your work done. That's your distance move or displacement. When I figure F, to calculate your F is 986 Newton. Right? All these are in two significant figures, so my want to round it off to 990 Newton. Right? So basically, conversion and conservation of energy, dropping a ball from a tall building. Initially, when it has zero velocity, so all the energy is potential energy, right? Or maximum potential energy. As the speed increases, kinetic energy increases, potential energy decreases as height decreases. Work done against air friction is transformed to thermal energy, Q in air. Okay. So at any time, you should be able to write total energy is potential energy at a particular height plus kinetic energy at a particular height plus a Q. Right? That's usually heat energy. Remember, height decreases, potential energy decreases. Potential energy depends on height. Kinetic energy increases as speed increases. Usually air resistance will increase as the speed increases. Work done against air resistance is transformed into heat energy. So that's a work energy equation. Energy conversion. Driving a car, usually you start with the petrol, chemical energy, convert to mechanical energy and heat energy. Mechanical energy is usually your kinetic energy. Conservation of energy, you have to write the equation. Chemical energy change to mechanical energy plus heat energy. Right? Heat energy is usually the work done against friction and air resistance. And energy conversion from the sun. Right? Sun thermonuclear reaction in the nucleus. The nuclear energy to radiant and heat energy. Right? So there are other forms of energy like heat, chemical. Right? We have done kinetic, potential, thermal we study later on, electrical we study next semester, chemical energy, and then nuclear energy. That will be third semester. This one we study in chemistry. So mechanical energy is usually kinetic energy and potential energy. So the principle is summarized. Principle of conservation of energy states that energy cannot be created or destroyed. It can only be converted from one form to another. Total energy in a closed system is constant. Right? I can write a formula form. Total energy, kinetic energy plus potential energy plus internal energy plus others. Other form of energy is constant at any time. U is usually called internal energy. We'll study later on in the semester. In any process, one form of energy is transformed to another. Okay, so we are more interested in this topic mechanical energy. Later third semester, we study about conservation of energy and mass, where we use this formula. Energy liberated, decrease in mass, times your speed. C is your speed of light. Total energy and matter in the universe is constant. There's no magic. Energy must come from matter, or matter must come from energy. Matter can be transformed into energy and vice versa. This law tells us that creation was completed at one time in the past. Right? Nothing is being created anymore. Application is for your info. When physicists were investigating radioactive decay involving beta particles, they find the particles after the decay had less energy in total than the particles before. So of course, you start questioning, right? Is the law broken? Cannot be. Law cannot be broken. So they guessed that there was another invisible particle which was carrying away the missing energy. Right? So if energy is not conserved, maybe there is another particle that's carrying away the energy. So most likely the particle is not charged. The particle was named neutrino, was proposed by theoretical physicists. So from your theory, right, we can forecast it because conservation energy. Then we can later on found it from experiment. Neutrino was not detected by experimenter until 25 years later. You can see that experiment takes time to detect neutrino. We can predict first on our theory. Okay, summarize. Rough ground means presence of friction. We have the applied force. Move the wooden block or car a distance or displacement x. So friction will always oppose motion. That's why it's always oppose the applied force. Work done by the applied force is the energy input. Right? This is the one that contributes to the energy input. Work done against friction, work done against that frictional force is the energy loss. This one doesn't benefit us. It's lost as heat. Gain in kinetic energy is the energy output. So the result of this force and friction, you have a gain in kinetic energy. And there's a work done. So work done, can summarize it, work done by applied force equals to work done against friction plus your gain in kinetic energy. Or write in formula form. Right? Force causes acceleration. Force causes an object to move a distance x, and the velocity increases to v. Where does the work go to? Okay, as I've said, the work goes to increase the kinetic energy and do work against the frictional force. That's why we summarize that. Work done against friction. Right? So that's the energy input. That's the energy output. That's the energy wasted. Right? Usually it's lost as heat. Right? As I said, summarize it, all that you have learned. Okay, let's do some question. Solving problem. This is your partial question. 2016. A pendulum bob which is attached to a string of length L is released at a position making an angle of theta with respect to the vertical. What is the speed of bob when it's at the lowest position? Right? Usually, draw a picture. There's your bob here. See as a point. There's a string of length L. Right? It will swing and it will come down to here. This is your length L. Right? You want to find the speed here. At this part there, the speed is 0. So it has potential G. Potential energy converted to kinetic energy here. So that is the maximum kinetic energy here, or maximum speed here. Okay, or just redraw that triangle as that. That's your height Y. This is your height H. So there's your L. Right? So your sine theta, your cos theta is Y over L, or Y is L cos theta. Right? That length there. So we want to find H. H is just your length. This is your L minus your that height there, Y, that height, Y, which is this one. Then we can apply our, treat this part as our zero potential G, this part as our maximum potential G, and this part as a maximum kinetic G. So gain in kinetic G, loss in potential G. Half mv squared mgh. That's your height. And take the square root of, cancel the m, take the square root, take a 2 across there, take the square root, get the answer. Here's your h with that. Answer is donkey. A block of mass 0.2 kilogram is hung at the end of a spring and is lifted vertically so that the spring is unstretched. The block is then released and it touches the table with a velocity of 0.8 meter per second. If the distance of the table from the release point is 0.1 meter, what is the force constant of the spring? Okay, sketch the diagram. This one is unstretched length. This is 0.2, same mass. There's your table there. That height there is 0.1 knot. This is unstretched. Right? So draw a picture there, can picture and have what is happening. And then you are told the block is released and it touches the table. So at this part there, where it touches the table, there's the speed. Right? So this mass there has stretched that distance there. Right? So write down the work energy theorem. Right? You start with potential G. Right? That one has potential G. Maximum potential G is lost. Right? Where does it go to? Gain in elastic potential G. This one is going to be stretched. That distance there. Right? So there's a gain in elastic potential G. It's going to have a final speed here. So it's going to have final kinetic G. So there's a gain in kinetic G. Okay. Write down equation. There's a formula for elastic potential G. There's a gain in kinetic G. Initially is 0. mgh. Right? Put in whatever is given. R. Right? Your extension. That's your extension. 0.1. Sorry, 0.1 square. Then your mgh. Right? For objective to do it fast, we don't need to use 9.8. We can use 10. Remember that we overestimate. Okay. So m, that's your mass. G, we use 10. But this for structure part, we cannot use 10. You have to use 9.8. Right? The height is 0.1. Right? Then this one, we take across. So it's half. That's your mass. That's your speed. Square that. And use your calculator to simplify. So it's the nearest one is that one there. You can use 9.8. It's just taking a bit longer time, that's all, but it doesn't matter. Okay, let's try a Cambridge A-level question. This is 2021 June paper 13. A car of mass 500 kilogram, it's a car, mass 500 kilogram, is at rest at point X on a slope as shown. So Cambridge usually like to draw a picture for you, help you understand, to picturize it easier. So at rest, initially no speed, the car's brakes are released and the car rolls down the slope with an engine switch off. At point Y, it's a point Y, point X, the car has moved through a vertical distance of 30 meters and has a speed of 11 meters per second. What energy is dissipated by friction forces when the car moves from X to Y? Okay, as always the case, write down the work energy theorem or conservation energy equation. Right? It has potential energy here. Where does it go to? It goes to work done against friction. It moves that distance there. And then it has no speed. It has a final speed there. So there's a gain in kinetic energy. Right? And write down in the equation form. mgh, that's your height. H, work done against friction. That's what we want to find. Right? The energy dissipated, that's the work done against friction. And there's a gain in kinetic energy. Put in your value. Right? W, take this one across there. Mass is 500 kilogram. G is 9.81. Can use 10 if you want to. Pi is 30. And half M, N is 500. Right? Final speed is 11. Final speed is 11. Right? Remember, we are taking over. That's why we got a negative sign there. So answer is B. Okay, let's do a partial question. STPM partial question. Structure question. 2014. A block of mass 65 grams. The block is placed at a height 8 cm above the top end of a long spring, which is fixed on the table as shown in diagram below, or is stretched. The block is released, falls vertically onto the spring. State the energy transformation of the system from the point of release to the maximum compression of the spring. Okay, this is unstretched, so it will have potential energy initially, and then as it compresses the spring, right, the kinetic energy, basically potential can converted to kinetic energy. As the spring is compressed, the kinetic is compressed to energy stored in the spring. So at point of release, the block has potential energy only. Right? No air resistance. Just before compressing, the spring has reached maximum kinetic energy as potential is transformed to kinetic energy. Right? It still has a potential energy, but it's decreased. As the spring is compressed, the kinetic energy and potential energy is transformed to store potential energy in the spring. Determine the maximum compression of the spring. Right? First, examiner try to help you. Right? That's why the examiner give you must know what is the transformation energy. Then can write down the equation. Loss in potential energy, gain in elastic potential energy. Right? Elastic potential energy is half kx squared. Right? Remember, this is the height, but there's also a compression there. So that is the total height of the block of wood. Right? It's compressed. So it's compressed a distance x. So that's a compression or extension. Right? Compression. Then put in your value. That's your mass. Sorry. Spring constant. Half x is what we want to find. That be X. Then M converted to kilogram. G 5.81. And that one, change it to meter plus your compression. Okay. Simplify it, take all to one side. If you want, you can simplify or can solve it from here. Divide by 33, get that equation. Then use your formula, calculate your X. That's your B. That's your C. A is 1. Win your value. Get 5 cm. Right? So X is the compression of the spring. Hi, Isaac.
Dạ, tôi
Alo.
mua cái chụp
Ai ai.
quay lộn.
Ok này đúng không?
Quá
Cứ nào, anh chứ.
anh rồi. Thì cái là một vài đứa anh ta mình chụp này. Sau after thì bằng đầu. Trong sáng thì mình đang chờ. Cái
Chụp thì thầy cái tiếng con đường đó. Kia đứng sẽ.
cái cách như vậy.
Qua tiếng có khi tiếng lượng tiếng mà khi ok đã tiếng hỏi là tiếng tiếng sắp đề này phải xây cái những khoản
Trời ơi, tụi một vài đứa con kìa, con cái như ra hãy chơi phải.
ok ra đó có người kia đâu cái đề tài đó.
Okay, let's go to our last part. Power 4.3. Derive this equation. Use the concept of efficiency to solve problem. Right? We have done that a bit for energy. Power is defined as the rate of doing work. Right? Differential equation dW dt. Or it can be rate of energy conversion. Unit, this one is joule. This is second, joule per second or watts. Scalar quantity. Right? If it's a constant work, constant force, then we use work divided by time. Right? Joule second. Right? To show how to derive it, object, force, there's your friction, there's your velocity. So if the force is balanced by friction, then it moves with uniform velocity. So that is your power, F is your force, V is your velocity. Suppose a force acting on the object causes the object to move a distance x in time t at constant velocity. Okay. So work done is force times your distance. Power is work done divided by your time. So work done is Fx, time is t. Right? So your xt is your velocity. V equals to x over t. T equals to F v. Right? You can draw a picture, help us understand how efficiency is the power input, that's your bulb. And then this power output and power wasted. Or we can draw, right? That's your device. It can be a turbine or a lamp. Right? That's your input power. That's your output power. And there's your power wasted. So conservation of energy, conservation of power, same thing, power or energy. Right? Input power, power output, power wasted. Efficiency is defined as power output or power input times 100%. Right? Efficiency is maximum at 100%, cannot be greater than that. That's what you put in is what you get out. That's 100%. For 100% efficiency, it means that the power output is equal to power input. Nothing is lost, nor wasted. Efficiency of device is usually less than 100% due to energy loss as heat or other form. Usually there's going to be friction. So work is done against friction. There's always presence of friction between moving parts. Thus, energy loss as thermal energy or heat energy. Let's finish off by doing example 4.3. Quick check in the book I'm using. Check 3, page 98. What is the power required by a body of mass m to produce an acceleration a when it is moving with a velocity v up a plane inclined at angle theta to the horizontal neglect system? Right? Draw a picture or picture in your head, in your mind, what is happening. Right? An object with velocity v up a distance x, object mass m. Assume the body is moving at constant speed. Right? If that's your distance, move up, then divide by time. And since it's at an angle theta, you must need to know that your sine theta is just your h over x. With the x across there, h is x sine theta. So power equals to work done by velocity, rate or gain in potential energy. Right? So this is your power input. Work done is force and velocity. Right? That's the gain in kinetic energy, this part there. Then because the body is moved to a high h, it must also gain in potential energy. And write in formula form, force ma times your velocity and rate mgh divided by time. Okay. H we can replace by x sine theta. Right? x over t is v. So we get that. The equation. Our answer is C. Okay, let's try next one. Have a go. Stop your video. Total resistance to motion of a cyclist on a level road is 25 Newton. If the speed is 12 meters per second, what is the output power? Right? Output power F times V. Right? That's the force. That's the speed. Then B. Cyclists managed to reduce the resistance to 15. Instead 25, reduce 15 by bending low over the handlebar. If the output power is calculated in A above, what would be his speed? Okay, same formula. FV, right? I've calculated, your total is the same power, 300. F is 15, and V is your 20. Okay, that's the end of our lecture. As I said, summarize all the formulas in one page. Then you can know what are the formulas you need to remember and try out the question. Okay, let's try solving some other problems. It's a A-level question. Power is transferred through a machine as shown. As a machine. Power input, power output, power loss. What's the efficiency? What's the answer? Right? Donkey. Your partial question. car moving with uniform acceleration from rest. The graph shows, I think we have done. The graph shows how the variation of power of the car with velocity. Right? Write down the equation. Uniform acceleration. The applied force is constant. Okay. And compare with the equation of a straight line. Answer is C. Formula with the equation of straight line passing through the origin. Okay. 2017, that's a partial question from STPM. An ant of mass 1.2 gram climbs up the mirror at an angle of 25 degrees from the vertical at a speed of 2.5 cm per second. The speed is in this direction as shown in the diagram below. What is the output power? That's your weight, mg. The applied force vertically downwards is your weight, mg. Calculate out. Right? Mass converted to kilogram and g. Right? As I say, objective is all right because we want an approximation times 10. We want to do it faster. That's your weight. Force and velocity must be in the same direction. Right? That's how we calculate our work. So force, right? Just using our force and velocity. That's our weight, which is our force. Velocity, right? 23. We want it in this direction. We want it vertically. So we resolve it. Cos 25. Right? So that's our answer. C. I will go at this one. Power station has an efficiency of 40% and generates 1000 megawatt of electrical power. What is the input power and the wasted power? Right? This is a Cambridge question, old question, 94 November, paper 1, question 6. Okay, if you got D correct, how to calculate efficiency, power output, power input times 100%. Right? You're given 40% output, that's the output, input, then take it, multiply, put your 40 down. Okay, so input, so wasted, that is a conservation energy. Right? Wasted is 2500 minus 1000. So that's why you get your answer donkey. Right? Let's have another one. A force of 1000 Newton is needed to lift a hook of a crane at a steady speed, constant speed. The crane is then used to lift a load of mass 100 kilogram at a velocity of 0.5 meter per second. How much of the power divided by the motor of the crane is used in lifting the hook and the load? It's 97, paper 1, number 6, November 97. Right? Use your G as 10. So draw a picture roughly as the mass of the load as the hook. So total weight as your tension. Right? So these two was the total weight equals to your tension. Right? Total weight is W. Is right? That's the hook. That's the hook. That's M times your G. Right? That's equals to your T. So for equilibrium, or tension or the applied force outwards there equals to your W. And power is T times V. Right? So T. So velocity or speed? Answer is B. Okay, we'll go at this one. An object is projected vertically upwards from the ground to a height where the object is stationary. Each ground brace represents the variation with height of the kinetic energy of the object, not air resistant. So it's very simple. Right? Remember potential energy, if you drop the object, it's going to be a straight line. Maximum potential energy equals to 0. Right? This one you throw it up. So when you throw it up, kinetic energy must be 0 initially. So it's kinetic converted to potential. So it's maximum kinetic energy converted to potential. So finally it will be 0 kinetic energy. Right? So it cannot be this answer. The answer is A. Okay, just remember your potential energy is a straight line. So when you throw it up, it has maximum kinetic energy. So you can straight away eliminate this answer already. Okay, for those who are A-level students, you may find more suitable will be when it's on Facebook. You can scroll up or scroll down to find your AS, the notes, PowerPoint notes. And this is a past year paper. Some of the years I've done it on PowerPoint. And then A2, okay, these are notes, PowerPoint notes. And then this is your A2 past year paper. Okay. In quite a number of years I've done it and then do it on PowerPoint. For semester 3, you may want to visit this Facebook page. Okay, for semester 3, semester 1 and semester 2 are the same Facebook page. Yeah, just scroll it up. You will find all the things there. Thank you for your time. That's the end of the lecture. Okay, have a good day. We will stop here. We end here.